You guys, what's up? Welcome back to the channel. So in today's video, we'll be talking about nucleophilic substitution, elimination, and addition. So let's talk about Sn1, Sn2, E1, E2, and addition. So Sn1 is dependent on the concentration of one product inside of one reactant, or it will have a very slow set. So Sn1, the rate is dependent on the concentration of one of the reactants, and that is your beginning molecule. For Sn2, the reaction depends on the concentration of two of the reactants, the nucleophile and the molecule at the same time. Sn1 has two steps. Sn2 has only one step, so it's kind of contradictory there. Sn1 is when your leaving group leaves first, so it will exit the molecule first before the nucleophile can attack. So that's why it's got only two steps. So it will leave and then it will attack it. And Sn2 is the other way around, so it's the other way around, but the nucleophile will attack it straight away at the same time as the leaving group leaving. So that's only one step. Well, Sn1 is two steps. Now, let's draw an example. So Sn1 are generally for molecules or with a lot of steric hydrogens, like tertiary carbons. For example, here we go. Now, this is a very good example. This is a tertiary carbon over here, and nucleophiles are very hard. Sn2s are very hard to, will most likely not happen because of a lot of steric hydrogens. Because if a nucleophile is to attack, they'll have to attack on the opposite side of this electronegative bromine here, because again they will repel each other, because they're both nucleophiles. They have slightly negative charge, very big steric hydrogen as well, so they're most likely to enter this way. But because of that, they will not react via Sn2, but rather this is Sn1. What happens is you have to wait until the bromine leaves, right, and then you form this carbocation, and this carbocation is stabilized by your three methyl groups pushing the electrons towards this, so it's more stable. And then your nucleophile will now come in immediately. So this is your intermediate here, very short-lived. Therefore, you've got your new product. Right, so Sn1, you can have either, so if you think about it, this carbocation here is in trigonal planar, right? And if you think about it, because it's trigonal planar, it's flat like this, right? Imagine this is your flat carbocation. Your nucleophile can come in and attack from this side or this side. So the product is non-stereospecific. So your nucleophile can be a solid bond, so out of the page, or it can be a dashed bond or into the page, so it's non-stereospecific. That means your orientation could be minus or positive, or S or R. So that's for Sn1, and you've got these energy diagrams where you need to know. Neat diagram. Nucleophilic substitution, or substitution reactions in general. Substitution reactions in general are very are exothermic. So your reactors will start here, you go up. This is what it would generally look like. This is your activation energy, by the way. Activation energy. This is at the start. This will be your, this will be your molecule here.
Br. This will be your intermediate, so C plus. And this will be your product at the end. Like that. Okay, this is Sn1. For Sn2, however, it is stereospecific, so you can only form one enantiomer. Well, let's say it's not really an enantiomer because you don't have a chiral carbon, but because you're attacking from the opposite end. So, for example, I've got H. B higher, the nucleophile will actually come on the opposite end, right? And because they're coming on the opposite end, for example, if this bromine here is out of the page, and this nucleophile will attach to the behind the page. So what I mean is you form this and attack at the same time. So this, you see here there are 2 steps, step 1 and step 2. Here this is really only 1 step, and it's just this. H, 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 and then this will come behind. Right, this is forward, this is behind. So you swap the so it's stereospecific because you can only provide, or you can only produce one enantiomer. And it's always the opposite because the nucleophile coming in will attach to the opposite end of your whatever leaving group you have. That's nucleophilic substitution. And the graph will just be like this. This is only one peak, like that. This activation to reactants products. You do get an intermediate carbon, a negative intermediate where all 5 of these are at the same time, but because that's really short-lived, right? And you know, it's not really significant to include in this particular energy profile diagram. Alright, so now we'll move on to elimination. Elimination will also involve nucleophiles, but nucleophiles act differently. So in substitution, they act as electron pair donor, and in elimination, they act as proton acceptor. So that's because of different roles. That's why you've got different mechanisms of reactions happening. So as you can see here, substitution. They are donating the lone pair of electrons in both types. However, in elimination, right? For example, you've got E1 and you've got E2 again. So E1's elimination 1, same thing. So this is when you form your carbocation first. For example, here, this is just right, same molecule as your substitution, but I just expand the CH3 up into the H's and C here. What you do is this guy will leave first, right? Then what you're left with is this. Here we go. This guy will leave on its own. You've got positive here. Nucleophile will come in and it will now act as a proton acceptor. Alright, so pull this away. This guy comes back here. There we go, this guy comes here. And then now you form this double bond now. H, H. There you go, this is E1. E2 is, however, the other way around because you don't wait for them to do so. You will attack as well. So your nucleophile will actually attack at the same time. As your leaving group is going. There we go. And again, you will still form the same thing over and over again but the main differences are that E1 is for, so for nucleophilic substitution, I forgot to tell you that solvent would also affect the rate of reaction happening. So polar solvents will affect Sn2. Yeah, because what happens is that if your solvent is polar, your nucleophile will most likely not attack your thingy, your molecule. So substitution reaction wouldn't take place. So for Sn2, your solvent needs to be non-polar. And for Sn1, your solvent needs to be polar to polarize your leading group further and make it easier to dissociate. And to break the bond, actually not dissociate, but to break the bond between the molecule and the leading group. You want the surrounding it's polarizable. So Sn1 will work better in polar solvents, and Sn2 will work better in non-polar solvents. Right. Now for elimination, however, as I told you, the elimination E1 is more fitted for larger molecules. So sorry, substitution 1 is better for larger molecules than substitution 2. It's better for smaller molecules, however. In E1 and E2, E2, they don't care if your molecule is large or not, E2, as long as your hydrogens are easily accessible for your nucleophile to attack. However, for E1, the size of your molecule still does matter, because actually the size doesn't matter, but because it's rather the carbocation form. In the meantime, like this carbocation here, if you've got this tertiary or secondary, it's more likely to happen at a quicker rate because of the stabilization effect of your methyl groups, or your alkyl groups in general. That's elimination 1 and elimination 2 as well. Right. So for elimination, you've got side-cell rules, so the opposite of your mechanical rules. Right, will make you remove the hydrogen from a molecule that doesn't have a lot of hydrogen in the first place. That is the side-cell